Hello, my name is Andreas Philipp. I'm in the IoT department at Keyfactor, and as a senior business developer, today I want to talk with you about the issuing of device identities in line with the IEEE 802.1 AR standard using our EJBCA CE version in combination with Node-RED, and we are using a standard IoT microcontroller from Espressif, the ESP32. Looking on our agenda today, I will talk briefly about IoT Lifecycle, IEEE 802.1 AR, so all the IDEF and LDEF stuff that is around in the world and to get a brief understanding. And then we are jumping into the demonstration and the showcase itself that we are preparing. All the source code and all the configurations and all the Node-RED implementation you will find in the Git repository, and the links are below in the video here. But let's talk a little bit upfront about the IoT lifecycle. So IoT lifecycle started, I think, in the end of the day when we are designing our IoT product and the ecosystem around this thing. Yeah, either it's a smartphone, it's a fitness tracker, or it is a PLC device in the industrial world. We have to design the whole system, we have to design the ecosystem around it. Then it comes to the bill of material, the definition, the PCB production. We have to build in the firmware and software into the system itself. And all this life cycle and the digital identity that are needed in this IoT life cycle are covered in the IEEE standard 802.1 AR. It's a very old standard. It's around for about now 10 years in the world because, yes, it started in our wireless LAN environment. So that was the time when we introduced wireless LAN in our hometowns, and maybe some of you remember that during that day, when you are firing up your wireless LAN router, it was in plain. Everybody could access to your wireless network. And then they were thinking about how to secure it, how to automate this, and one proposal was this standard itself. It's based on the usage of a trusted module, TPM technology, but nowadays it will be reactivated because it covers the whole life cycle of an IoT device, in issuing the device identity and also provisioning the device itself into operator's environment. When the device comes into the field, it has to be provisioned into your network itself, has to be connected to your ecosystem, has to be connected to cloud services, and therefore also the digital certificates are needed. And all of these methods, issuing device identity, provisioning into the ecosystem in the operational side, all of these methods are defined and specified in the IEEE 802.1 AR standard. It's a very old standard that's around for ages, but it's now coming back into our mind because it covers a whole IoT lifecycle, a typical IoT lifecycle, imprinting the device identity and provisioning this device identity in the operational network. That is, everything is covered in this, perfectly covered in this standard itself. And what we are showing today is a typical scenario how to implement this standard, this piece of paper, into a real world, into a real IoT device itself, that is not, I think, configured and designed for security purposes. That's a standard $4 IoT device, perfectly used or heavily used in our environment. It comes with wireless LAN, Bluetooth, perfectly equipped, easy to program, and The challenge for us and what we want to show you today using our enterprise, our EJBCA Community Edition, how to implement the IEEE 802.1 AR standard. Here's an overview how it looks like in an ideal world. On the manufacturing side, we have the manufacturing CA issuing in the first step the device identity, the IDEF ID certificate, into the device that is imprinted during the production. That must be absolutely clear, and that is what we also see here, that this device identity, this IDEF ID, is imprinted during the production process, issued by the manufacturing CA. Then the device is shipped into the user and operator environment and domain, and therefore the LDEF ID, so-called LDEF ID, from the standard is issued by the operator CA. Therefore, the device identity that was issued during the manufacturing time is validated, and after the validation, the LDEF ID is also issued by the operator CA. And then with this LDEF identity, we can start provisioning the device into the services like Azure, Amazon, cloud services, but also into MQTT brokers or OPC-UA environments in the industrial world. That's a typical scenario. Okay, here we have the overview of the production process that we implemented in our permanent showcase that we are operating at Keyfactor at the Campus Schwarzwald in Germany. It's a permanent showcase where we are showing on-demand production for IoT devices, and we are implementing an OT environment. So in the first step, the user is ordering in a web shop the IoT device, and he can select it, the 3 different kind of version of these devices. The order is shipped from the web shop to the ERP system in the typical IT environment. The ERP system is generating a production trigger and send this to the MES system that is located in the OT environment, the OT network itself. And then from the MES system, the production process is triggered, the on-demand production is triggered. And in combination with the control computer in the OT environment, the IDEF ID is generated and is imprinted into the device during the production. And then after shipping the device to the user, it is provisioned into their security domain and into their operational domain itself. So let's start with a deeper look into what happened into the controller, into the IoT device itself, and what's implemented. On the right-hand side, we have the device manufacturing domain. That's the domain where we are issuing and imprinting the initial device itself. On the left-hand side, we have the operational domain. That is the domain where the personalized IoT product is provisioning into the Wi-Fi area and is provisioned into the cloud services and cloud or services that they want to hook up, like an MQTT broker on OCSP server. Let's focus on the device manufacturing domain. That is also the topic for today's tutorial here. So in the ESP32, we implemented a partition table that is based on a factory partition and a trust store that is permanent data storage. This trust store is secured by an RES symmetric key, and here all security relevant credentials like IDEF ID, LDEF IDs are stored in a protected area. We have built in, or we have programmed a small personalization app that is preloaded into this IoT device, and that comes with a fixed IP address into the device network. It comes with IDEF ID key pair generation, It comes also with the IDEF ID certificate signing request generation, and it also has the capability to store the finally issued IDEF ID into the trust store that is implemented into the ESP. I will later on go into the details about how the workflow itself is triggered and how Node-RED is used here for design or for implementing a workflow to connect the device itself. From technology reason, we are using embedded TLS in the ESP32 as a crypto library, and all the functions are built in based on this library itself. And yeah, that's it. So first step. I think in the first step we have to set up and install our PKI history. Therefore, I refer to the existing video. One is from Sven, how to install the PKI infrastructure and get it up and running in the Docker container, in the Docker environment. And the second one, please go through it, creating the PKI history with EJB-CA, creating a root CA, creating a sub CA or an issuing CA underneath. Please go to these videos and then you are setting up the environment. Based on this infrastructure that you installed, here are the specification of the root CA that we implemented. For this demo here, we are implementing a root CA with a SHA-512 with RSA key material. The validity of the root is 5 years, and the subject are implemented as defined here. The sub-CA, same specification, and same specification, and it's also implemented in a standard way. Please use these scenarios for implementing the PKI, because otherwise we are running in trouble later on. Then in the next step, create your IDEF ID and entity and certificate profile. We are starting with the certificate profile implementation in EJB-CA. We are using key algorithm is RSR 2028, 2048-bit key length, or 4069. It's also a possibility. Please set the validity in the certificate profile to an infinity validity, because that's something that the standard is specifying, that the IDEF ID, the initial identity of the device, is infinity. How to do this? Please enter the validity that you are setting the year on 9999, the month on 12, and the day on 31. That's the infinity certificate. Key usage standard for digital identities is digital signature and key encipherment. The certificate profile and the end entity you will find also in the Git repo of this tutorial itself. The end entity is also straightforward. We are defining a common name, organization, organizational unit, and what's special for us in this use case here, or how we implemented this, that we need a serial number, and the serial number is generated by the MES system. That's normally standard, that the serial number is not generated by the device itself, that is generated by the MES system, who has all the parameters, and it is here mandatory in this certificate and entity definition itself. When it comes to the typical 802.1 AR implementation, the standard is based on the usage of a trusted computing module, the TPM. This is a standard IoT microcontroller with no security features and functions and TPM built in. So we decided To expand a little bit the specification, and we have added a description field in the certificate itself, where it says we have a software trust or a hardware trust. And we are using here, in this case, a software trust implementation and not a hardware trust implementation. Uniform resource identifier, also optional, but normally use them, because we have to know where to connect afterwards when it comes to services and cloud identities. Step 3. So after defining and implementing the entity profile and the certificate profile, we should start enabling our REST API in our community edition. Therefore, we are going into the system configuration and the protocol configuration, and we are enabling the REST certificate management API, so that this REST API is accessible from outside. To access this interface, we have to add a client server authentication mechanism, and therefore we have to issue a REST token, which is used in the personalization phase itself, and which is used also to access the certificate REST API functionality. We are generating an append token for the REST API, and we are adding this token to the role members for using this REST interface itself. Therefore, we are going into the role management functionality of EJBCA. We are adding a new role with the name REST API, and then we are adding the issue token by using the common name that we are chosen during the generation of this REST token itself. Please edit the access rule for this token through the role template RR administrator. Select the authorized CA that you set up before in the step when you're setting up the issuing CA. Then select the add entity rules, and here we only need the rule create something. We don't need rules like delete or edit or revoke or whatever. We only need the creation rule, and select the end entity profile, and that's the end entity profile that we generated before for the IDEF idea. And that is the typical scenario how to configure this REST API. For testing, and this interface, we could also provide you some basic REST example based on Python. You find the link down below to GitHub where you find the repos, and with the admin token that you issued, you can easily see if it's possible to access the REST interface itself. Step 4. Creating the production workflow. As I mentioned before, and we are using a control computer that is triggered by an MES system to start to communicate with the device and the ESP controller during the production process, and to trigger the key generation on the controller itself, and then generate the CSR and requesting the certificate from this production CA itself. Therefore, we are using to implement this workflow, we are using Node-RED as a workflow engine itself, and that is running on the control computer. And here we have a brief overview of the workflow and the flow charts. And if you want to have a look in detail, please also refer to the Git repo where you have the PDF file, and you can dig into the process itself and step by step what happened on which time and how to see this implementation in Node-RED itself. But this gives you a typical overview how such an imprint process could be designed. And this is not a showcase scenario here. This is a real production scenario that we are imprinting. that we are implementing at our permanent showcase in the factory at Campus Schwarzwald. One specific configuration that you have to take into account and that I want to address here is when you want to access our PK REST API of the EJBCA from Node-RED, which is possible with standard board tools in Node-RED, because you are using the standard HTTP request nodes, you have to split out the issued REST admin token that we issued before into a key file and a cert file. It's a little bit tricky, but that's the implementation what we see today or what we have today in Node-RED. So Node-RED isn't able to use a standard P12 file, and we have to pick up the P12 file, export it, the key material, export the certificate, and both files have to be uploaded into Node-RED itself. Configuration, I think it's standard, so we are defining the methods that we want to use, and then we are using our standard REST commands that are defined by EJBCA itself. That's a whole workflow that we implemented that is running, and I don't want to go through it in details, but in the end of the day, we have different kind of building blocks. In the upper building block, the trigger block is exactly there where the MES command is coming in and says, here, there's a new production. Then into the next step, Node-RED is waiting to see the device itself in the network, and once the device is in the network, we are starting the key generation process. We are starting the certificate generation, or certificate signing request generation in the network. And then in the gray building block, we are generating the enroll P10 REST command to EJBCA, and we are connecting to the PKI itself. And with a response, we are sending it back to the device, and then the IDEF ID, it's imprinted into the device itself. That's a whole workflow. Very complicated, many nodes to maintain. And that brought us to a point where we thought maybe we make it a little bit easier, and we are providing to the community some tools to connect directly to the CA itself. And that is what we did. And we developed a Node-RED contrib EJBCA package where all of these, or we are combining a set of nodes in Node-RED to access directly the EJBCA REST API. We also supported now P12 files, so you don't have to split any P12 into different kind of key material file. You can directly load your file into the node itself. And when we are supporting our standard CE, EJBCA CE REST functionality, enroll P12, we are generating CSR locally. We can search and get status for a certificate from a PKI, and that are built-in nodes, and also the link to the contribute file here you find down in the description below. We are working now on an implementation of a USB HSM in Node-RED so that we are securing the key material also in this unsecured environment. But this is work in process, and if you like, you can set a on a regular, you can come back to our Git repository and see if there are some updates available. And I think in 2-3 months, the HSM support will be also there. And we are supporting a cheap standard USB HSM. Let's recap. So we are talking today, or we are talking in this workshop about the production PKI and how to set up an IDEF ID certificate profile and identity into EJBCA. I showed you how to enable the REST API and generating the access token. We saw, or I give you a hint that this access token, if you want to implement or import it into Node-RED standard workflows, you have to split it out into key file and certificate file. We designed the whole configuration and personalization flow in Node-RED, and we triggered the key generation in ESP32 and the CSR generation. And with the CSR, the EJBCA is issuing the device identity and it's imprinted into the device itself. And last but not least, some hints for the CSR generation in ESP. We are using embedded TLS. That's a standard library that I used, and that is perfectly working in this environment. On that point, we want to thank you for your attention, and any question, here are our contact details and links to the documents, source codes, and repos you find below. Thank you.